Let's get started. So, hi, I'm Shadaj, and today I'm going to be talking about Scala, power, and versatility. Power is the ability to do complex tasks easily, and versatility is the ability to do a wide range of projects. And Scala is excellent at both of these. For the past few Scala Days, my presentations have been more or less a show and tell of what I've been doing for the past year, and this talk is no different. But you'll see a theme throughout all the projects I show today of this power and versatility that Scala gives us. We'll be going from SBT plugins to bioinformatics in the browser to distributing bioinformatics algorithms all the way to a primitive home automation system. Let's get started with the first project, Google CodeJam. For the past few years, I've been participating in the Google CodeJam contest. It's a computer programming contest run by Google in which you progress through multiple rounds in which you solve computer programming problems. So there are multiple problems in each round, and each problem gives you a different number of points. Now, you're trying to get a certain number of points to advance to the next round. And everyone's vying for a spot in the final rounds held at some Google office. In Google CodeJam, you're allowed to use whichever language you would like. You run your solution to each problem on your own computer. The way Google handles this is you download an input file, run it on with your computer program, and submit it to Google servers for checking. Now, with this submission process, it can get a little bit tedious. So I built an SBT plugin to automatically submit solutions to Google CodeJam contests. Let's take a look at the manual submission process for Google CodeJam. You start by downloading the input file. Then you modify your code to match up with the name of the input file. The reason you have to do this is in Google CodeJam, if you solve a problem incorrectly, you can try again. But when you reattempt a problem, you get a different input file name. So you have to make sure you're reading from the correct input file. You run your code. This will output to a set output file. You upload your output file. Now, just like your input file name changes, your output file name will change as well. So you have to make sure you're uploading the correct output file. You zip up all of your source files. To prevent cheating, Google requires that you upload all of your source code. Then you upload your source files. And you have to do this for every contest, every problem, every input type. And in CodeJam contests, I want to focus on solving the algorithm, not figuring out how to submit my solutions. How do we get around this? I started by looking around the internet, seeing if someone had already created a way to automate this submission process. Google actually provides a command line tool for Google CodeJam written in Python, but there are a few things I didn't like about it. The first thing, it requires you to store your Google account password in plain text. Now, I didn't like this concept of just storing my password in a file that if someone else gains access to my computer, they can read it. And on top of that, even if you have two-factor authentication, the command line tool bypasses this by having you generate an application-specific password. Now, this application-specific password allows other people who gain access to that text file to use other parts of your Google account. Another thing I didn't like about this was it didn't integrate with the tools you used for actually coding up your solutions. For Scala and Java, you could use SBT, but this tool doesn't integrate with those tools. So you have to manually run your solution and still modify your code because the CodeJam command line tool doesn't do that for you. So I developed a tool for SBT. So now all you have to do is boot up SBT and type in GCJ DRS, which stands for download, run, and submit, your problem ID, A, and the input type, small. Let's try it out. So I'm going to go ahead and switch over to Qualification 2014. So this is the project I used during the 2014 qualifications round. I already solved these problems during that round, but now I've updated those to become an example project of using this plugin. So I'm going to go ahead and boot up SBT. Let's start by seeing how well I did in that contest. I'm going to use the command gcj status, which gives the user status in that contest. I'm going to go ahead and run that. The way I bypassed this plain text storage was to handle your password in memory. And I actually don't even store your password. I only store the cookie Google sets when you sign in. And to get that cookie, I have you use a JavaFX web view. So it's just as if you're on a website and you get an OAuth pop-up to sign into your account. Here now you have a JavaFX web view that you sign into your account. So I'm going to go ahead and sign in. And I use two-factor, and since this is all running as if it's a normal Google sign-in, I can type that in as usual. So what just happened there? Let's go a little bit up. So after we signed in through that JavaFX web view, it started by extracting the cookie. So it taps into the JavaFX web view and gets that Google cookie that we then use to call CodeJam APIs. Then we get middleware tokens. So these are our cross-site resource forgery tokens that we use when making API requests to CodeJam. Then we exchange the cookies for those middleware tokens, and we also print out the expiry date. We get the contest status and contest problems, and I'll explain what these mean in just a bit. And then we display the user status, so we can see which problems I got correct, which problems I got incorrect, what I didn't solve. Now let's go ahead and actually submit a solution. So this, after contests occur in Google CodeJam, they move into what's called the practice mode. So you can still submit solutions to that contest and test out your solutions. So I'm going to be using that mode here. So I'm going to be solving magic trick. So I'm going to go gcj drs, and the ID for this, since this is the first problem, it's A, and I'm going to be solving the small input. I'm going to go ahead and run that. So if you scroll back up, what happened was it started by downloading the input file, then it ran my solution. My solution printed out all of these logs, and then I can submit. And I got it correct. Let's take a look at how this all works. When I first typed in that command gcj status, it took me through the entire flow of logging into CodeJam servers. I didn't have to run a command to first log into Google, then log into CodeJam servers, etc. It took me through the entire flow needed to run that command. Now to implement that, I split up this process into multiple substeps. And these are represented by different states. The first state that we start out in is not logged in. At this point, the plugin has no idea who you are, and you're about to start the process. Now to get to the next state, not logged in has to open up a JavaFX web view and have you log into your Google account. This is all run asynchronously with futures, and we'll see in a bit how futures make tying in these different steps throughout our flow so much easier. But to start, we're in not logged in. We use the JavaFX web view to get into logged in Google. So now we're logged into Google servers, but we're not yet logged into CodeJam servers. For the next step, we have to get our middleware tokens. Once we do that, then we go into logged in CodeJam. Now we're logged into the CodeJam server, but we haven't yet initialized our users' participation in the contest. To do that, we have to do two things. The first is get contest status. This returns us a code which represents if the contest has not yet started, if it's running right now, or if it's in practice mode. And this allows us to know which APIs to call when submitting solutions. The other thing we have to find out is the contest problem. So we use getContestProblems, which returns us a JSON of all of the problems within that contest. And we use this when submitting solutions to correlate the ID, which is A, B, etc., to the actual ID that we use when making those API requests. And we end up in the contest initialized state. So at this point, we've completed the entire login flow, and now we can run the commands we expect from this plugin. So we have our download, run, and submit, and this is also split up into individual tasks, and we have GCJ status. Let's take a look at how this was implemented. To implement these different states, I have a trait login status. Now each of these states implements this trait. And when you're implementing the trait, you're required to implement first these three methods: as logged in Google, as logged in CodeJam, and as contest initialized. Now these return futures of the respective types. The really cool thing we can do with this is, since we have these monadic operations on futures, we only have to implement the logic to get to the next step, but nothing else. So for example, let's say we're not logged in. We only implement as logged in Google. We only implement the logic for that, but in as logged in CodeJam and as contest initialized, what we do is we get as logged in Google and then run a flat map of going to the state we want. So for example, the implementation of as contest initialized would be as logged in Google dot flatmap underscore dot as contest initialized. So this would delegate to the necessary logic to get to that step. Another thing we want to do in this plugin is we want to cache the highest state we've been in. So for that, we have greater than, which takes another login status, and this allows us to know dependencies between different states. Let's take a look at how we make requests to the CodeJam APIs. For handling requests, in this plugin I use Dispatch, which is a great library, and it allows you to tie in to all the other parts of your tool by giving you HTTP requests in the form of futures. So here, what I'm doing is I'm getting the middleware token. So I start by logging that I am getting the middleware tokens. Then I create my request path. GCJ base represents the base URL for the Google CodeJam server you're connecting to. In the past, Google has run CodeJam on different servers for special events, such as the one they did a few years ago to win a ticket to Google I/O. So I take whatever my GCJ base is, and I take the path underneath that called middleware. I make a request to this. I make a GET request with a few query parameters, and I add the Google cookie that I got from the JavaFX web view. Now I make an HTTP request to this, I parse it with play.json, and I get it as an option of token response, which contains all of the data from that JSON result. And if I can't parse it, I throw an exception, which then gets logged as an error within SBT. Scala makes handling asynchronous tasks so simple. When I talked about getContestStatus and getContestProblems, which are needed for going to the initialized state, neither of these two requests that we have to make are dependent on the other. So you can run these in parallel. And to run it in parallel, it's as simple as zipping the two features together and getting a feature of a tuple of the types of those features. That's all we have to do. And this is the power of Scala. You don't have to dive deep into your logic for handling asynchronous tasks. You have all these tools at your disposal to work with asynchronous tasks, and it makes it so much easier. This is all the implementation I had to do as contest initialized. That's it for creating a Google CodeJam plugin with SBT. Next up, let's talk about bioinformatics. Last year, I presented Janalgo, which is a bioinformatics library for Scala. It allows us to perform analysis on biological sequences, but the core feature of Janalgo is it allows developers to view biological sequences as plain old Scala collections. They actually extend index sequence. So you can expect all of the functions you would see in any other Scala collection. You can do your map, flat map, fold, whatever you expect. It's all there for those biological sequences. But you still have the ability to keep the data compressed since you know what are the elements like, etc. What I worked on for the past year was adding a lot more features to Genalgo, but the biggest feature I added was the ability to run bioinformatics algorithms in the browser. Genalgo now supports Scala GS. Let's try it out. So this is a demo taken directly from the Genalgo website. At the bottom, we have this demo, align sequences from Uniprot. So this is a two-step demo. The first part of this is we're going to make a request to Uniprot's API. Uniprot is a universal protein database. We're going to get those proteins, and then within the browser, we're going to align them. So I'm going to pre-fill some values. So this is a protein that shows up both on mice and humans. I'm going to hit align. So this just went to Uniprot from my laptop, got those sequences, and aligned them. And here we can see what are the similarities. So star means that they're identical, colon means there's a mismatch, and space means there was an insertion or a deletion. Now this required no JVM. There's no backend server. This is all running on GitHub pages. And what we're doing with this is we're allowing to take bioinformatics to a whole new level in the browser. Let's take a look at how this was possible. Now, when porting Genalgo, which started out as a JVM-only library, to Scala.js, there are a few things I had to watch out for. The first thing I had to implement was cross-platform networking. Now, for the example of Uniprot, I had to make a request, but I didn't want to copy the code for making those requests to Uniprot between the JVM and Scala.js. I wanted the same API to make requests to be available no matter what platform you're running on. So to do this, I created a trait request maker. This represents an object that can make requests on our behalf. You implement a method get, which takes a URL and an execution context to run it in, and it returns a feature of string, which is a response text. Now in JavaScript, we implement this with the DOM extensions ajax.get. So you make an AJAX request and get the response text and return that. On JVM, we implement an object with the same name so that the shared code can access this object. Here I'm using dispatch to make the request, and I get the response text here as well. Another thing I had to watch out for when I was porting this library to Scala.js was handling resources. On the JVM, handling resources is super easy. Whenever you publish your library, all of the files within SRC main resources are packaged along with it, so any libraries that depend on that have those files included with it. With Scala.js, your resources aren't packaged along with the JavaScript when you publish a library. So to handle this, I wrote up a simple method in my build.sbt to generate Scala objects that represent files. And this shows the power of Scala. You don't have to create an external project that acts as a command line tool to generate this. This is written within my build.sbt, and I can hook it into a source generator, so then this automatically runs every time I compile. To see what this would do, let's say we had a file foo.txt with the lines ABCD and 1, 2, 3, 4. When we ran this source generator on these resources, we get a file resources.scala, and we'll have a val foo. And the contents of this value is a list of the lines within that file. So here we get a list of ABCD and 1, 2, 3, 4. So now we've designed a way to handle resources no matter if we're on the JVM or JavaScript. There's one more thing I want to show you guys. This is a JavaScript only feature. it allows us to render proteins within the browser. So in my biology class, I was to present about diseases caused by genetic mutations. So I decided to choose the sigma-1 gene. The sigma-1 gene is known to cause juvenile ALS. So I did a little bit of research into what mutations occur, and I got two models of the non-mutated and the mutated proteins. So here I'm using Scala.js and Genalgo to live render these in 3D. So here we can actually see the difference. If we go over here, we have this chain that links the coil to the rest of the protein, but here the coil is broken off from the rest of the protein. And I could embed this within my biology presentation and show them right there on the spot what was changing between these proteins. Let's take a look at how this is done. To render these proteins with WebGL, I use a PV, which is a protein visualization library for JavaScript. The really great thing about Scala.js is it allows super easy access to JavaScript libraries. Now this is all the code I had to write to render one of those proteins. I initialize a viewer, and that takes an HTML element, and I also pass it a viewer setup that provides things like how much time to spend animating in that protein. Then I make a request, ajax.get. Now this is Scala.js DOM extensions. I parse it, I assign a helix sheet. This allows us to draw the secondary structure, so that's the color-coded coils and arrows. Then I render it with the cartoon function, and I auto-zoom. Now the really cool thing about this is even though we're using a JavaScript library that's dynamically typed, all this code is statically typed. So if you give anything other than an HTML element here, you will get a compile time error. So you don't have to worry about getting undefined is not a function anymore with Scala.js. And Scala.js still allows you to write up quick hacks really easily. So here, when I'm rendering, I'm not using any settings yet. So being too lazy to implement that trait to handle the setup for rendering, I can just give it a dynamic .literal, so that's an empty JSON object, and that's all I have to do. So you're not required to write up these facades. They do make it compile time easier because it will give you compile time errors, but if you're trying to get something done quickly with Scala.js, you don't have to do it. So that's the real power of Scala.js. Now to implement these facades, here's the viewer facade. It extends JS object, and all I have to do is list out what methods I can call on it. They all return js.native, which means that Scala.js should pass it on to the native JavaScript library. And that's all I had to do. That's it for Genalgo with Scala.js. This year, I was in the STEM class in my high school. In the STEM class, we're trying to promote science, technology, engineering, and math. And in this class, I was to present a project at the Synopsys Science Fair. So the Synopsys Science Fair actually took place last week. And for my research project, I decided to do something in the area of bioinformatics. I'm really amazed at how much structure there is within our cells. So I decided to do my research project within bioinformatics. Now one of the algorithms that intrigued me in bioinformatics was the sequence alignment algorithms, in which we compare biological sequences. Biological sequence alignment algorithms are used in a variety of contexts. They're used both in the research and the medical fields, but they're very slow. For sequences of length m and n, it takes big O of mn time to calculate the alignment. And when you're working with massive DNA sequences, this can get very slow. So I worked on applying distributed and concurrency techniques 2 sequence alignment algorithms to make them faster. Now with distribution comes Akka. And with Akka, who could be a better mentor for my project than the tech lead of Akka, Dr. Roland Kuhn. So it was a lot of fun to work with him on the project, and it made the project even more successful. Let's take a look at the original algorithm for sequence alignment. In the original algorithm, it's a dynamic programming algorithm with a 2-dimensional matrix. So we start by calculating the seed value. This is just, we initialize it to 0. And to calculate all of the other values in this matrix, each value is dependent on 3 of its neighboring values. So for here, those 2 values, they only have 1 neighboring edge, so they're both dependent on that 1 cell. So we calculate those 2. Now next, we have that cell. Now in this cell, we do have those 3 neighboring edges. So we once those 3 are calculated, we can calculate this cell. When we're running this algorithm with large biological sequences, this can get very slow because it runs sequentially, calculating values 1 by 1. And with large matrices, this can get very slow. What I noticed was because of this 3-cell dependency, we can actually split up our matrix into blocks. And these blocks can be calculated in parallel. Now the reason I'm doing blocks and not calculating cells in parallel is because, especially on distributed systems, you have latency. Now you have a trade-off. You can either increase how much you parallelize this algorithm by reducing the block size, but that also introduces more latency because you have more communication between nodes within your system. So I split up this matrix into blocks. So let's take an example run through of this algorithm. We start by calculating this block. Once that block is calculated, we can calculate both of these blocks in parallel, and this is where the speed up comes. Once we calculate those 2, we can calculate these 2 blocks. Once we calculate these 2 blocks, we can calculate this block. Once we calculate that, we're done. So now we have calculated the alignment of biological sequences in parallel. To implement this algorithm, I used 2 contexts. The first was a multi-core system. In here, I have workers running on CPUs and a master running on the processor. So the workers calculate the values within these blocks, and the master coalesces them all together into the large matrix at the end. Now in a cloud system, it's a lot similar, except now we have 1 machine for the master and individual machines for each of the workers. On a multi-core system, handling the communication was very simple. We didn't have to send over biological sequences. We could just send memory addresses to everything since they're all running on the same machine. But on a distributed system, we can't send memory addresses and expect them to work. So to handle that, what we do is we send sections of biological sequences over the network that the child workers will need. And so we send what section of the matrix the child worker needs to calculate, and a child worker sends back that section, which we then add into our larger matrix. Let's try it out. So here I'm going to be running the implementation of this algorithm via features. Features are showing up in every single project I'm talking about today because they allow for creation of a dependency structure. It's so simple with features. You just specify what the feature depends on and it automatically propagates as values are calculated. So I'm going to go ahead and run, and what you guys are going to see is going to show up in the top left corner, and it's going to go a little fast. But you'll see that instead of calculating blocks 1 by 1, we're going to be calculating them in parallel, which creates kind of a diagonal pattern. So I'm going to go ahead and run this after it compiles. So here, now you can see we're calculating all of those blocks in parallel. So instead of going 1 by 1, we're going a lot faster. And at the end, you can see the CPU saturation, which allows us to finish quickly. And this shows the path that we take when backtracking through the matrix. Now, when I just ran it, I ran it with the thread.sleep to show you the parallelization so you can see those individual blocks being calculated. Now let's comment that out and run it to see how fast it actually gets. So here you can see now we're blasting through that matrix and we're done. So that's distributed alignment. So let's take a look at how this was all implemented. In future alignment, I was just gushing about how amazing futures are in creating this dependency structure, and it really is super awesome. To express dependency on the left and top blocks, which I need to calculate another block, all I do is a for comprehension on those two blocks. Once I have those two, I align the next block, and that's all I had to do for every single block in my matrix. Now for the distributed implementation, I implemented this with Akka, and this is how the actor communication looked within my systems. So we have our distributed actor parent. This is running on the master machine, and we have one actor system running on each child machine. Now this actor system will contain multiple distributed actor children, as well as a distributed actor store. So we'll get to distributed actor store in just a bit, but first let's talk about the communication between the parent and the child. Now the parent sends a build matrix command to the child. It contains which block is needed to be calculated, as well as information about the edge values, which are needed to calculate values within that block. The child goes, calculates this, and sends back a command, build matrix done, once it's finished. Now, as I talked about earlier, with distributed systems, you have a little bit of complication when it comes to handling biological sequences, because we can't send memory addresses anymore. What I do to handle these biological sequences is I have an extra actor, distributed actor store. And distributed actor store is a middleman of getting these biological sequences. So distributed actor child, when it calculates a block, it first asks for the sections of the sequences that it needs. So it asks get sequence 1 and get sequence 2. Now distributed actor store will check, do I already have it? If so, it sends this back immediately. Otherwise, it asks distributed actor parent for it. Once the store gets back the sequence from the parent, it caches it locally and then forwards it to the child that initially requested it. Let's take a look at how this whole communication is implemented. In the child, this is the code when I initially receive a build matrix command. What I do is, since we don't want to run into dead letters when we're using sender within a future, I store my sender here in requester. Then I ask for sequence 1 and sequence 2. Here again, they're run in parallel by doing zip. And once I get those two, I send myself a message with that build matrix command. So this is getting back onto the queue of messages to process with the sequences as well as the original requester. Now in store, to handle these get sequence commands, I first, again, just like in the child, I store my requester since I'll be handling it within a future. I check if my cache doesn't yet have a promise in store. So the way I'm handling this cache is I have an array of promises. Now the reason I'm doing promises instead of just storing the sequences is if we have two requests to the same section right next to each other, we don't want to make a request and then make a request again if we don't have a sequence in our cache. What we want to do is we want to see, has a request already been made? And then listen to when that request is finished. So here, if we haven't even made a request, then we form a request. And then we take that request, get the future out of it, and pipe the result to the requester. In distributed parent, what we do is we calculate the start and end indexes of this sequence that we need to send back to the store. And since Janalgo biosequences are just plain old Scala index sequences, we can use slice to get that section. So we don't have to do any fancy stuff to get those sections. We can just use all of the Scala collection functions we're comfortable with. Now, I ran all of these. I had fun getting set up with EC2 for the first time. So all of these were run multiple times to ensure scientific accuracy, and here I have the results for both concurrent and distributed alignment. So in concurrent, I'm getting almost 7 times faster with 16 cores, and with actor concurrent, I'm getting very similar results. With distributed, here with 32 machines, we're getting almost 14 times faster. But one thing you'll notice is, what's up with that obscurant graph that slows down at the end? This is an artifact of calculating block sizes based only on the sequence lengths. So here I'm taking the sequence lengths, running them through a function, and getting the block sizes. One thing I want to do in future work is to also take into account things like latency between the nodes, as well as how many machines are running within my cluster to calculate these block sizes. That's it for bioinformatics in the cloud. Lastly, let's talk about play. A few years ago, I saw Brad, which is Berkeley's ridiculously automated dorm. It's truly ridiculously automated. That guy has a button on his bed to put his room into instant party mode. That's just awesome. And so I was really inspired by this, that you can do so many cool things with automation. So I decided to start building my own primitive home automation system, which I called Ash. What I'll be showing you today of Ash is a very, very primitive home automation system. It's actually not even automating anything in my home yet. It's commanding applications that run on the same system you make a request from. Right now I only have one way to control it with your voice through a web application, but I hope to expand this in the future, such as maybe hooking up a Raspberry Pi to your wall and controlling it with touch gestures, or even more. And this is something I expect to be working a lot over the summer. So let's take a look at the control flow of Ash. In Ash, you start out in your Chrome browser. That's how it is for now, but eventually you might have other sources of input. No matter what you get your request from, it goes to your Play server. So the Play server is the core of Ash. It's what handles all of the requests. And then Play can connect to other services. Right now, Ash can connect to AppleScript to command locally running Mac applications, as well as the cloud. And because everything within Ash is asynchronous, again, futures. Every single project here is futures. So here again, because everything's asynchronous, these two can depend on each other. So we can get data from the cloud and use that in AppleScript. And that's actually what we'll see in our demo. So I'm going to go ahead and open up Ash. Now what I'm going to do here is I'm going to be playing a song on Spotify using Ash. So I'm going to make a request to play a song. It's going to go search up that song on Spotify through the web APIs. Then it's going to use AppleScript to play that song. So let's try it out. Ash. Ash. Spotify play song maps. And now we're playing music through Spotify, controlled through a voice interface. And we can do a little bit more. Ash. Spotify pause. And now Spotify paused. That's Ash. Let's take a look at how this is implemented. At the core of Ash are services. Ash is built on top of a plugin architecture where you drop in jars that represent different services. So for example, Spotify is a service. Now when you implement a service, you extend this trait service, you give a command prefix. So this would be something like Spotify, which tells Ash to route the request to this service. And you also implement async execute, which takes args, which is everything after your command prefix, and returns a future option of notification. So this future will succeed if it was able to process that command, and it can optionally return a notification to display. Now you may want to interface with other services, so I provide things like AppleScript, which has execute, which takes a script and returns a future of the result. And so I use Scala processes to run this script. And I put these together in Spotify service. So this is all the code I had to write for the demo I just gave you here. This is play song and the song name. So we start by generating a URL. This is the URL to the Spotify API that we want to make a request to. I use play web services to make a request to that. Then I parse it with play.json. I get the first track and I make a Spotify AppleScript request. That's this thing down here. And once it's done, I map it to a notification that I am now playing that song. So you can see here how features are making it so simple. I can flat map on a feature, return an option, just everything flows together. That's all the projects I have for today. Here are the links for the projects I showed. And I hope you can see now how much power and versatility Scala gives you. We went all the way from Google CodeJam plugins for SBT all the way to a home automation system, going through a bioinformatics library for the browser. And we were able to use the same language for distributing algorithms in the cloud, running them in the browser. So that's the power and versatility of Scala. I can answer any questions now.
You might have mentioned this, but what are you using for voice recognition?
Okay, so for voice recognition, I am using the WebKit recognition API, which has support for both offline, and it can also connect in Chrome to Google servers to do voice recognition. So this is the same API that's used to power things like OK Google and other commands you might use within your browser for voice recognition. Any other questions? Okay, thank you.